In this module, we're going to take a look at typical construction features of the power generator and also discuss important factors related to operation and control. The purpose of the generator is to receive the rotating mechanical energy which is produced in the turbine and convert this into usable electricity at a specified terminal voltage. This diagram shows the major components of a typical generator, including the stator, iron core, stator windings, rotor, bearings, coupling to the turbine, the exciter and exciter coupling. The stator is anchored firmly to the concrete bed. The electricity is actually produced in the stator winding, which is the stationary winding which is supported by the stator frame. The stator winding consists of insulated copper conductors which are embedded in the slots of the stator core. The slots run end to end. The so-called iron core is made up of laminations of special steel. Each individual lamination or plate is coated on one side with an insulating material, the objective of which is to reduce the flow of induced eddy currents in the core. This in turn reduces the production of heat in the iron core and thus keeps its temperature down. The laminations are tightly packed together and secured within the stator frame. Once the stator bars are fitted into the core slots, they are joined at the ends to form continuous coils or windings. These end connections are referred to as end turns. The conductors are securely held in the slots by wedges of insulating material. This is extremely important, as the windings are subject to quite heavy mechanical forces during operation. The windings may try to twist during heavy power surges or electrical faults on the power system. Similar distortion of the windings may occur if the generator is incorrectly synchronized, that is, connected to the system when it is out of phase with the system. One problem that can occur on generators is the loosening of the windings with resultant vibration and increased temperature rise and perhaps damage to insulation. Checking the conductor wedges for tightness is an important maintenance item during overhauls. The stator conductors are connected together in various series and parallel arrangements to produce the rated terminal voltage, typically in the range 11 kilovolts to 25 kilovolts, and rated output current, which may be several thousand amps. The stator windings are connected to the terminals, usually located at the bottom of the generator. Outgoing conductors are connected to these terminals in order to carry power to a bus or a power transformer, and perhaps to an auxiliary transformer. Voltage transformers, or VTs, are also located close to the terminals to provide input to the generator voltage control system. Current transformers, CTs, are usually located close to the terminal bushings. These CTs measure the value of current and transfer this information to the control and protection system. In some generators, surge capacitors or lightning arresters are located at the terminals to protect the generator windings. Heat is produced within the generator in three ways. Current flowing in the stator winding produces heat, which is proportional to the square of the current. This is the I squared R, or copper loss. Friction between the spinning rotor and the air, or hydrogen, in the generator produces heat called windage loss. Stray induced currents in the iron core produce heat called iron loss. If the internal temperature rises too high, it will damage the insulation and put the generator out of service. For this reason, distinct limits are placed on permissible temperature rise. In order to monitor this, temperature detectors are embedded in the stator windings at the anticipated hotspots. These readings are continuously recorded and alarmed when necessary. Forced cooling is employed to keep the temperature rise as low as possible, either by hydrogen cooling or air cooling. We'll be talking more about this in the next segment. But first, let's move our attention to the rotor. The function of the rotor is to provide a rotating magnetic field. the rotor is coupled to the turbine and thereby receives all of the mechanical energy produced. This mechanical energy is then transferred across the rotating magnetic field to the stator windings, where it is converted into electrical energy. The rotor is supported at each end by journal bearings. These must be very accurately aligned to maintain the same precise clearance between rotor and stator all the way along the length of the rotor. A forced lubrication system is required for the bearings. Pressurized lube oil may be provided from the turbine lube oil system, or in some cases, a separate generator lube oil pumping system is installed. So the rotor provides the rotation, but where does the magnetic field come from? Well, the field could conceivably be provided by a permanent magnet, but this arrangement would provide no means of control, and the field would probably not be strong enough. In actual fact, the magnetic field is created by a rotor winding. Insulated solid copper conductors are embedded in rotor slots, and they are connected in such a manner as to form a huge coil which turns with the rotor. DC current is passed through the rotor winding in order to produce a magnetic field with a north and south pole. Of course, the next question is, where does the DC come from? Well, there are two possible sources depending upon the design of the machine. A common arrangement is to provide DC from a rectifier located in a nearby panel. This is known as static excitation. The DC is applied to the rotor winding through brushes running on collector rings. An alternative source of DC excitation is from a generator, which may be driven by direct coupling to the shaft, or in some cases through a reduction gearbox. Access is provided to allow maintenance and inspection of the collector rings and exciter. We'll be looking at details of different excitation systems later in this module. Generally, in modern installations, the generator rotor is directly coupled to the turbine shaft and runs at 3,600 or 3,000 RPM. But what is it that determines the actual speed requirement? We'll be talking about this later. For now, let's take a break and please switch off the tape and review this material in your workbook. The cooling system is a vital component of generator operation. As we mentioned in the last segment, the amount of power which a generator can supply is limited by the temperature rise of the windings. Therefore, the more efficient the cooling system, the greater the load that can be placed on the generator. For small turbine generator installations, air cooling is employed, usually open cycle. The air is actually circulated through the generator by fans, which are fitted at each end of the rotor. As the rotor spins, the fans provide the force to circulate the cooling air through the rotor and stator core. Cooling ducts are often built into the rotor and stator core to allow passage of cooling air. This diagram shows a typical arrangement. Air is drawn in from atmosphere and passed through filters to remove any particles of dust or other contaminants. The air is then drawn down through silencers into the fan impeller at each end. The air is exhausted radially from each fan under pressure and is directed to follow the desired cooling path, eventually exhausting to atmosphere. In some units, silencers are fitted to the air exhaust as well as the inlet. Usually, a separate cooling system is provided for the exciter or collector rings. In this particular arrangement, a small fan impeller is fitted into the collector air inlet adjacent to the collector rings. Air is pulled in through a filter to circulate through the terminal connections and collector rings. As we can see, this system is self-contained and requires no attention from the operator other than to ensure that the filters are clean, thus allowing sufficient air to pass. The pressure drop across the filter will indicate when it needs to be replaced. On standby or peaking units, this task can easily be performed when the unit is out of service. However, on continuously operated base load units, automatic continuous filter cleaning is usually installed. The provision of clean air is absolutely essential, as the ingress of dust and other particulate matter may block cooling passages and may even cause grounding and consequent damage to the insulation. Where the generator is located in a hostile environment, say very dirty conditions, a closed cycle air cooling system is usually employed. In this case, the same air is continuously circulated through the unit, and the air itself is cooled as it passes through a water-cooled heat exchanger. Because of the additional pressure drop across the heat exchanger, it may be necessary in some generators to add a circulating air fan. Makeup air, to compensate for any leakage, is admitted into the suction of the circulating fan. Filters are provided on the makeup air inlet from atmosphere. In other designs, the shaft-driven fans are made larger to avoid the need for a separate air circulation fan. With this arrangement, makeup air is drawn in through the generator housing by these fans. Well, so much for air cooling. Let's now turn our attention to hydrogen-cooled generators. When the unit size increases above, say, 100 megawatts, hydrogen cooling is normally employed. There are several advantages to using hydrogen as a cooling medium instead of air. Hydrogen is less dense than air, and consequently the windage loss, that is, friction loss due to rotation of the rotor, is considerably reduced. Hydrogen has a much greater capacity to absorb heat than air. Therefore, it is a better cooling medium. The generator operates in a very clean atmosphere. Generally speaking, the hydrogen-cooled generator can be made physically smaller than an equivalent air-cooled generator of the same capacity. Therefore, on the larger capacity generators, it is more economical to install a hydrogen-cooled system, even though this entails a much more complicated installation. The generator casing is built as a sealed unit, with the hydrogen inside the casing maintained at a pressure of about 30 psig, or about 3 bar. Not all units operate at the same hydrogen pressure, so make sure that you know the operating conditions for your particular unit. Actually, the higher the hydrogen pressure, the greater the cooling effect, and consequently the power output of the generator can be increased. The hydrogen is circulated within the generator by shaft-mounted fans, similar to the arrangement for air-cooled generators. The heat picked up by the hydrogen is extracted by passing the gas through water-cooled heat exchangers. Some adjustment of cooling water flow through the hydrogen coolers may be necessary to maintain the optimum temperature for the hydrogen gas. This is normally performed automatically. As the hydrogen is maintained at a positive pressure inside the casing, there is no possibility at all of air entering from outside. This is a distinct advantage, as it ensures that the generator internals operate under ideal, clean conditions. On the other hand, the presence of hydrogen under pressure does have a slight negative factor, that is, the loss of hydrogen by leakage. Leakage could conceivably occur through joints in the casing, particularly around the terminal bushings, but the most likely area is through the shaft seals, and we'll talk more about this in a moment. Generally speaking, the loss of hydrogen is very small, but this still needs to be compensated. Makeup hydrogen is added through an automatic pressure regulator, which is set to maintain the desired internal hydrogen pressure. The hydrogen manifold may be fed from hydrogen bottles or perhaps from a hydrogen tank installed in the plant. In order to prevent hydrogen leakage around the shaft, hydrogen seals are fitted inboard of the bearings at each end of the generator. A common type of hydrogen seal consists of spring-loaded seal ring segments which lightly hug the shaft under spring tension. The segments are lubricated by seal oil, which is maintained at a pressure of about 5 psi above the pressure of hydrogen inside the generator. Consequently, it is impossible for hydrogen to leak out past the seal. Seal oil leak-off is then drained back to the seal oil pumping system. Any hydrogen that may have been absorbed by the oil is drawn off by a vacuum pump, which forms part of the seal oil unit. This small amount of hydrogen leakage is then discharged to atmosphere. The seal oil pumping system is a very important part of the generator operation. It must be placed in operation before the generator starts to rotate on turning gear and then maintained in service at all times. A decrease in seal oil pressure will be alarmed, and the operator must take immediate action to rectify the situation. Usually, a standby seal oil pump is installed, and in addition to this, a DC emergency pump is provided in case of the loss of AC auxiliary power. Are there any dangers involved in handling hydrogen? Well, the answer is yes and no. For example, a small leakage of hydrogen into atmosphere presents no danger at all, as the hydrogen is completely diluted by the large quantity of air surrounding it. Also, at the other end of the spectrum, pure hydrogen cannot ignite, and so presents no danger. However, certain mixtures of hydrogen and air do present an explosive mixture. The danger area for an explosive mixture is within the range of 5% to 75% hydrogen in air. For this reason, it is extremely important to maintain the purity of hydrogen inside the generator. Ideally, the hydrogen purity should be above 97%. Purity is continuously monitored and indicated, and alarmed if the level falls below the set point. But you may well ask, if the hydrogen comes from hydrogen bottles, how can it be other than pure? Why is it not 100%? Well, the fact is, each bottle of hydrogen does contain perhaps a minute quantity of air, and this eventually accumulates inside the generator. I'm sure that those of you who already operate hydrogen-cooled generators know that with time, the purity does begin to fall. In order to raise the level of hydrogen purity, it is necessary to purge the generator. That is, to vent gas from the generator to atmosphere and replace this with new gas directly from the hydrogen bottles. In this manner, we are exhausting gas which contains, say, 96% hydrogen and introducing gas of, say, 99.8% purity in its place. This will improve the average purity in the generator. So all of this ensures that we keep the gas mixture well above the upper explosive limit. But what about the mid-range? Well, this potential problem occurs when the generator is shut down for maintenance and we need to open it up for inspection. How can we discharge the hydrogen without it coming into contact with air in the explosive range? The problem is resolved by eliminating the possibility of hydrogen and air coming into contact with each other inside the generator. First, the generator is purged of hydrogen by filling it with carbon dioxide, CO2, under pressure. CO2 is a completely inert gas that is non-flammable and non-explosive. The CO2 gas is admitted under pressure through a manifold at the bottom of the generator casing. This gas is much heavier than hydrogen. As it fills the generator casing from the bottom upwards, it slowly pushes the hydrogen out of the top manifold. The correct valve arrangement must be selected by the operator to allow this top manifold to discharge to atmosphere instead of receiving hydrogen from the bottles. The vent is usually located at a high point of the plant, and there is no danger as the hydrogen is immediately diluted by surrounding atmosphere. During this process, the gas inside the generator casing is monitored, and when this indicates close to 100% CO2, air is admitted via the upper manifold to clear out the CO2. Now remember, carbon dioxide presents a suffocation hazard when encountered in a confined space. The total time required for purging may take several hours. When the generator is to be readied for service, then the reverse action takes place. Initially, the generator will be full of air. CO2 will then be admitted at the bottom manifold to push the air out of the top. When all air has been expelled, hydrogen will then be admitted from the top manifold, forcing CO2 out of the bottom. This is quite a tedious process and requires much care and attention from the operator. Make sure that you learn the specific procedures for your particular generator. Of course, for a short overnight shutdown of the machine, where generator maintenance is not required, the generator remains charged with hydrogen with the seal oil system in operation. To prevent excessive leakage from the seals, it is important that the shaft rotate continuously on the unit turning gear. It is quite apparent that operation of the hydrogen cooling system is much more complicated than generator cooling by air. You must become thoroughly familiar with the operating procedures for your particular installation. On large turbine generators, additional cooling is provided by passing water directly through passages provided inside the actual conductor bars. As the conductors are operating at high voltage, insulated connectors are needed to transfer the cooling water to and from the winding. For the same reason, only high-quality, low-conductivity water must be used, say condensate or demineralized water. A cooler is normally employed to remove the heat in this closed-cycle system. In this segment, we've dealt with the fundamentals of the different cooling systems. Make sure that you thoroughly learn the details of the specific cooling system which is installed on your generator. At this point, it's time for a break. Please switch off the tape now and review this material in your workbook. So far, we've been looking at details of construction of typical power generators. But how does the generator actually produce electricity? Now, I'm sure you'll all remember going through this subject in study of basic electricity, perhaps several years ago. But do you still remember, say, the difference between single-phase and three-phase power, or the significance of increasing or decreasing excitation, and what is meant by reactive power? We feel it will be worth our while at this point to review generation fundamentals, to lay the foundation for our discussion on generator control. This simple AC generator consists of a coil or rotor rotating in a magnetic field. The magnet has north and south poles, and its magnetic flux passes through the rotor. By convention, the lines of force or flux leave from the north pole, pass through the rotor, and then return to the south pole. So the lines of force at the south pole are set up in the opposite direction to those at the north pole. In this diagram, as we start rotation of the coil, one side passes close to the north pole and one side close to the south pole. The coil sides cut the magnetic lines of force and in doing so create a voltage in the coil. This is the well-known principle of electromagnetic induction. When a conductor cuts a magnetic field, a voltage is induced in that conductor. At 0 degrees, the coil is not cutting any magnetic flux at all, and therefore the induced voltage is 0. The value of induced voltage is maximum when the coil is in the 90-degree position, because here we have the maximum rate of cutting magnetic lines of force. The direction of induced voltage in the purple conductor is opposite to the voltage in the red conductor. The voltmeter, therefore, receives the sum of the two voltages. As the rotor moved from 0 degrees to 90 degrees, the voltage has increased like this. And then as the rotor moves from 90 to 180 degrees, it decreases like this. As the coil continues rotation past this 180-degree position, the conductors are cutting flux from a different pole. The red conductor is now closer to the north pole, and the purple conductor is closer to the south pole. So the voltage generated is now in the opposite, that is, negative direction. So we can see that one revolution of the coil produces one cycle of alternating voltage. It is called alternating because one half of the cycle is in the positive direction and the other half is negative. We have been moving the coil with the magnet in a fixed location. This is basically what's done in the brushless exciter, which provides the excitation voltage or rotor voltage for some AC generators. Now, this will be discussed in segment E of this module. However, this is not a practical arrangement for large AC generators, as huge slip rings would be required to accept the large AC generator output current from the rotor. Instead, the magnet is rotated while the coil remains fixed to produce an AC voltage. One of the principal tasks in designing an AC generator or alternator is to construct a combination of magnetic fields and coil configurations that produce a true sine wave at the generator terminals. If we connect this circuit through a resistance and an ammeter, we find that the current follows the same pattern as the voltage. The positive and negative half cycles mean that the current is flowing in one direction for half the cycle and then in the opposite direction for the other half cycle. As the magnet continues to rotate, it produces further cycles of voltage and current like this. These curves are known as sine waves, and values can be calculated from trigonometric tables. This then is how AC voltage and current are generated. You can see that for each revolution of the magnet we have one cycle. So if the rotor is spinning at, say, 60 revolutions per second, then we will generate 60 cycles per second. You recognize this, of course, as frequency, usually stated as 60 hertz. 60 revolutions per second is equal to 3,600 revolutions per minute. And I am sure we are all familiar with that number. By contrast, a two-pole machine on a 50 hertz system, as used in Europe, needs to run at 3,000 RPM. On some generators, the rotor is built with 4 poles instead of 2. That is, 2 north poles and 2 south, like this. Now, each single revolution of the rotor will generate 2 complete voltage cycles. So at what speed will the generator need to run in order to produce a frequency of 60 hertz? This can easily be calculated from the standard expression that says frequency equals P, that is the number of poles over 2, times N, that is revolutions per minute over 60. In this case, the 4-pole machine must run at 1,800 RPM to produce 60 hertz. You can see that the required speed of the generator depends upon the frequency and the number of poles on the rotor. In practice, instead of a rotating permanent magnet, the magnetic field is provided by an electromagnet. The rotor winding is a large coil, and this is fed with DC to create the north and south poles. The DC field current is known as excitation. Increasing the magnitude of DC current increases the strength of the magnetic field up to certain limits, and vice versa. Now let's look at various ways of connecting stator windings. In this basic arrangement, the 2 ends of one stator winding are brought to the generator terminals and then connected to feed a single-phase load. In order to generate a second voltage, we can use an additional stator winding, which is placed at an angle of 120 degrees from the first winding. An AC voltage will also be generated in this winding, and it too can be connected to feed a single-phase load. But note, their generation cycles, that is, minimums and maximums, occur at different times. In fact, the voltage cycle of phase 2 is 120 degrees behind phase 1. That is a time lag of 5.5 milliseconds on a 60 hertz system. In a similar fashion, we can utilize a third stator winding, which is placed yet another 120 degrees, that is a total of 240 degrees from phase 1. This too can be connected to feed an individual single-phase load. And similarly, its voltage generation cycle is 240 degrees out of phase with phase number 1. So what we have in effect here are 3 independent windings supplying 3 independent loads, but each using a common iron core and rotating magnetic field. Almost 3 generators in one. But there is a further advantage. By connecting one end of each stator winding to a common neutral point, we can provide one single return conductor for the circulation of current from all 3 phases. As the currents in these three phases are out of phase, the positive and negative flows in the neutral occur at different times, and therefore have a tendency to cancel each other out. In fact, if the load on each phase is identical, that is, a balanced load, we find that the return current in the neutral completely cancels out to zero. Therefore, we can eliminate the neutral. We now have the conventional three-phase system as you know it. The three outgoing terminals from the generator are connected by three lines to the three-phase load, that is, the bus or power transformer. This, in turn, feeds the three-phase power system. Most of the heavy loads on the system are actually three-phase balanced loads. For example, electric motors. Moreover, single-phase loads, such as residential loads, are connected to the distribution system in such a way as to provide an approximate balance. The common connection of the stator winding, usually known as the neutral point, is often connected to ground. There are several other ways of connecting generator windings, but this is certainly beyond the scope of this module. If you would like to know more about this subject, please refer to our other programs. So let's now turn our attention to synchronizing. When the generator is switched into the power system, it is not sufficient to just close the circuit breaker. Certain definite conditions must be set up before the generator can be synchronized to the system. The first thing is that the generator must be running at its rated speed. This is done by adjusting the governor set point. Second, the generator terminal voltage must be adjusted to equal that of the bus to which it is being synchronized. This is done by adjusting the excitation. As the strength of the magnetic field is increased or decreased, so will the terminal voltage rise or fall. The third very important factor is that the incoming generator voltage must be in phase with the bus voltage. What do we mean by this? Well, look at this example showing one phase only. Here is the sine wave representing the bus voltage, and here, superimposed, is the incoming generator voltage. You can see that the generator is over 90 degrees out of phase. If we closed the breaker in this situation, the generator would attempt to pull itself into phase. Now, this could twist the windings in the stator core and create considerable damage. Of course, the great surge of power would be detected and the breaker immediately opened by protection devices. In order to provide the correct conditions for synchronization, we need to very gently adjust the speed of the incoming generator so as to bring it into phase with the bus. At the moment that the two are in phase, the breaker should be closed, and the unit will then lock into synchronism with the power system. On most modern units, this synchronization is performed automatically. However, you may find the need to do this manually on certain occasions. For this purpose, a synchroscope is provided. This is connected to either side of the breaker and, in fact, indicates the difference in phase between the two sides. For example, this condition shows that the generator is 90 degrees out of phase with the bus. As the pointer is stationary, it also indicates that the speed, that is, the frequency, of both the system and the incoming generator are identical. More often than not, you will see the pointer slowly rotating like this, indicating a slight variation in speed. In the case shown, the incoming generator is running slightly faster. If the rotation is slow enough, you can manually close the circuit breaker just before the pointer reaches the midnight position. The machine will then lock itself in synchronism and start providing power. In order to further increase power output, it is necessary to add more torque to the unit. This is done by increasing the steam flow to the turbine. But can we not also increase real power output, that is megawatts, by increasing excitation? The answer is a definite no. Increasing the excitation will only increase voltage to a certain extent and will also increase the reactive power output of the generator. We'll be talking about this later. Let's first take a break, and then we'll come back and continue our discussion with a look at generator control. For now, please switch off the tape and review this material in your workbook.